פרופסור יוסי מרט מאוניברסיטת חיפה. יוסי עשה את התואר הראשון והשני שלו פה באוניברסיטה העברית, ואחרי זה דוקטורט בטקסס, ב-A&M. עבד תקופה מאוד ארוכה גיאולוגיה של מחצבים. לפני 45 שנה עבר לעבוד על גיאולוגיה וגיאופיזיקה ימית, והוא הציג לנו היום סמינר על התיאוריה שלו למודלים של טקטוניקה ואבולוציה של קור קומפלקסס.
תודה רבה. I'm quite excited to teach in this room. I used to teach here mineral ore deposits some years ago. What I want to talk about is oceanic core complexes, which is a very strange association of rocks at the ocean floor in very distinct locations. So, and the talk is based on mostly, my part of the talk is based on analog experiments. And so I'll talk a bit about analog experiments of transform faults and analog experiments of subduction. Then I'll talk about oceanic core complexes. The work on transform faults was done in the laboratory in University of Rennes in northern France. And the idea is that there is a box of about meter on meter filled with honey, with density 1.3 gram per cubic centimeters, and there is an internal frame. Half of it is fixed and half of it is mobile. The experiment, there is a layer of honey, then there's a layer of silicon putty, and there is a layer of sand above. So the sand behaves like a brittle material, this is plastic, and this is fluid. So we have a rough model of the upper part of the Earth, and the mobile part of the upper box, inner box, it can move in any direction. You can put the stepping motor either here and push or pull, and there are rails which drive this box. Can we scroll over the light? This experiment box looks like this. I'm sorry about the lines. My hands were shaking, but it's about 2 centimeters by 2 centimeters in each box. And there's the scale here. And that's before the experiment begins. And here I show extension, almost normal. And the rift develops from one side and propagates to the other. And if you will, it doesn't look very different from the Reykjanes Ridge, which starts from Iceland and goes all the way to latitude 55, approximately, with no transform faults at all. It's continuous rift, like this, and it's wide at the top and getting like a knife edge at the bottom, which is very different from most oceanic ridges, which have the ridge and many transform fault and fracture zones. But when we applied oblique extension to this cake of sand and silicon, we get a simultaneous system of depressions. I marked them in red here, 1, 2, and 3, and 4, and 5, and 6. And in time, as the deformation continues, and the deformation is about a centimeter an hour, slow deformation, we develop something like some cells, some basins are connected, But there's an initial transform fault, and this is a mature transform fault. And the mature transform fault is derived by lateral motion here and lateral motion here, so that they have the transform fault. And the length of the transform fault doesn't change, or doesn't change much, between this edge and this edge. These are stable in space. The plates move to the left and to the right, but the transform fault is stable. Until recently, it was commonly accepted that the motion along transform fault is pure, and it's only lateral motion, but a very interesting paper that was published in Nature by Jason Morgan and his team showed that there is oblique extension along the rift, and the rough morphology of transform fault is derived from the oblique extension and some mantle rock accretion along the reef. It's not only motion, but also accumulation of new material from the mantle. The green dots here and here is the location of the oceanic core complexes, provided that the spreading rate is very slow, and I'll explain it later. But these are the facts. Another thing that affected my research was a visit of the ocean drilling program into the Eastern Mediterranean, which Floyd McCoy and me initiated. And we drilled 3 boreholes, a transect, from Eratosthenes Seamount to Cyprus. The borehole in Cyprus was also only material from the island. It wasn't very interesting, nothing surprising. This was surprising. One point I want to add is the motion of northeast Africa northward in this part, on our part of the plate, is about 1 millimeter a year. Here it's 5 millimeters a year. Here it's 25 in Anatolia. Anatolia moves westward very fast. So the motion here is complex because there is a drive northward and there is a drive westwards. And this is a trace, more or less, of the subduction zone. And what we get, if you take the boreholes and put them on the levels, let's straighten the seafloor. The yellow is the Messinian, the pink is Miocene, pre-Messinian, and the green is Eocene Senonian. This is the Cretaceous. Aptian was found here. So it looked as though it could be some sort of an anticline here or some sort of an anticline here. But when we correct for water depth, it looks totally different. The accumulation, the outcrop of the older rocks, which we identify as the anticlinal axis, is found here at depths of 2,500 meters. Which means that Eratosthenes Seamount is being subducted under Cyprus. That's what made it so interesting. And we didn't expect to find something like this. We didn't expect to find something like this. When it comes to subduction, we tried to work in a model, in a laboratory with analog modeling in Sweden. And it started with Mart, who hosted Chris Talbot, the head of the laboratory in Uppsala many years ago. He came to take a look at Mount's dome, and you introduced us. And I told him that I want to do an experiment on subduction because I don't understand what's going on. So Chris was very polite and he listened to what I had to say. And he said, I don't think you'll get anything out of the lab, but if you have time and money to spend, you're welcome to come. So I came, and Anat Einat Aharonov and Liran Goren participated in this research. And we started, the theoretical part was that if we have initially a rift when an ocean is formed, the fault at the boundaries would be normal, steeper or milder, but it will be normal. And there will be a part of the lithosphere floating on the asthenosphere. Therefore, the load of the lithosphere of the continent will be lighter than the load of the oceanic part. Therefore, there will be a concentration of stress in this point and this point. When the ocean opens, we'll get, this part will drive under the continent. There'll be rotation of the fault from this direction to this direction, and only at a certain stage there'll be motion along this fault, and all the earthquakes and the volcanism that occurs there, I'll talk about it later, and there'll be a split in the mineralogy, and some of the minerals will become serpentinized, which is lighter and will bring material back to the surface. And some will become denser with eclogites and will dive into the asthenosphere. This is the model from a recent paper by Taras Geria. The red is the cooler and the yellow is the hotter. The normal thermal gradient from Earth to asthenosphere along the lithosphere is about 30 to 40 kilometers, 30 to 40 degrees per kilometer. In the subduction zone, because we insert cold material back into the mantle, the rate is about 10 degrees to kilometer, and in some places even less. And a paper by Onit Kessel and her co-workers shows the effect of water in the mantle, considering the melt of basalt and the clinoparoxene. And we see that the dry material, the boundary between the solidus, dry material increases, the temperature of the dry material increases with pressure, but when the material is wet, there's a huge drop in the solidus until it goes up again. And there is also a mineralogical alteration from the pyroxene with density of 3.2 to 3.5 gram per cubic centimeters to garnet, which the density is much higher, from 3.6 to 4.5. So we get, when the material goes down, a depth of about 40 kilometers, 50 kilometers, some of the pyroxene turns into garnet, it becomes denser, and then it dives into the asthenosphere, otherwise it cannot enter the asthenosphere. I put some concept or data about the serpentine group, which is this is the general formula, and X could be magnesium or iron or aluminum or nickel or manganese and others. It's very versatile mineral group, and it contains several major groups: the serpentine and antigorite, and the lizardite and the chrysotile, with the extension here. But the point I want to show that here, the forsterite, the olivine, when the presence of available silica and water, will produce serpentine. Whereas without water, the pyroxene will produce garnet. This is not the both formula. No, this is not. This is unbalanced. I got confused with the numbers. This is the picture of how it looks in nature. The black is a peridotyte, and this is a serpentine asbestos. In this case, this is from the Troodos in Cyprus. The asbestos, and you see that the ultra basic rock and the serpentines are tightly packed together. And here you see a piece, fragment of rock with some micaceous minerals from the schist family, and large pieces of garnet. The coin here, go back. The coin here is about 1 inch in diameter, 2.5 centimeters in diameter. These are quite big. So I traveled to Uppsala in Sweden. In Uppsala they have a very large and fast centrifuge. It's about 2 meters across. It had all sorts of possibilities with affecting the sample, but most of them, when I was there, didn't work. I understand that now they upgraded it again. Originally, it could go to 6,000 RPM, which is about 8 to 9 G, and 8 to 9,000 G. And when I was there, it worked only to about 1,200 rotation per minute, and the gravity increase was 1,000, about 1,000. The experiment was run on a box, I'll show you in a minute, where we had something that resembled the asthenosphere, oceanic ductile and brittle, and continental ductile and brittle. The interesting thing is that the densities are not very different from nature. Definitely the same order of magnitude of nature. If we say that the continental crust will be about 3 grams per cubic centimeter, the oceanic a bit more, this is 1.5. The difference is negligible when you take, for instance, the viscosity, where the difference between experimented nature is 15 orders of magnitude. To say nothing about the time. So this was the basic setup of the experiment. And I want to show you some results. What we tried to do is to build the subduction arc. Subduction arc was once a very hot topic, where it started with someone who pressed a ping pong ball and could produce a round depression, and they said the arc is like someone was pressing Earth, planet Earth, like a ping pong ball, and produce the results. We tried to play with friction. So there is one piece of experimental material, and here is another. We put some Vaseline here. The blue line marks it. And nothing here. As experiment, this is a time per second. 1,000 G acceleration. And you see that it starts to be a bulge here after 1 minute, and it grows, and it grows, and it grows. And there's also extension in this half of the experimental box. While here, the pieces collide. So if we take look at sections, and this is the last stage, and I'll show section B and C. This is B when you see the denser slab goes under the lighter slab, and there is extension here. You can get things getting thinner. At this part where there's no friction, or there's a high friction, there's very little subduction and the unit gets thicker because of the compression. The same box. Same box. Everything's the same except one drop of Vaseline here. And I want to argue that the serpentine acts as lubricant in nature, and it enables motion, where you see large motion in the serpentine or the similar water-carrying minerals act to reduce the friction, and when there's no friction, we get compression. It's the same other parameters, and we get extension and compression along a single subduction zone because of the mineralogy. Here, please concentrate. I want to do a thinking experiment. This is an oblique view of the experimental box. The red line separates surface from section. So look at it, and if you concentrate, you can see it, that this rises towards you and it glides here and it glides here. So on surface, we create a back arc basin. The extension, this part of the continent is torn from the main part. If you want, like Crete in the Aegean Sea, if you want, like Japan, I don't care. It's torn away and we get a back arc basin. And there is subduction that runs and operates the entire deformation. And this, the yellow line, marks the initial contact between the lighter and the denser slabs. This is the result of numeric experiment run by Chemenda when he was in Grenoble. No, he was in France, in southern France somewhere. And he published several papers on subduction, experiment, analog and numeric. And what he tried to do, to argue, is that the ophiolites come in and come out of the subduction zone along the same subduction channel. Here it goes out, and this part is torn and returned to surface. This is, he wanted to argue about the structure, basic structure of ophiolites, and brought also some samples from that, but I tried to argue that subduction shouldn't be exactly like children when they go out the way they came in. It can also have a Caesarean section, and material will come here, will change mineralogy, and there'll be faults or cracks that enable material to go up, and every a change in the depth of these cracks, there's cracks that enable material to come up to the surface, will have different temperature and different pressure. Therefore, the lithology will be different, and we'll get rhyolites here and andesite here, and when you're out of the subduction system and you get some material coming from the upper mantle to the surface, you get results. And in Eilat and in the Sinai Peninsula, you see places where you have the rhyolite and the andesite very nicely cleared, and Aryeh Shimron wrote his PhD about that. So, what do we know about oceanic core complexes? Oceanic core complexes are known to occur near the intersection of slow mid-ocean ridges and transform faults. They are mostly built of primarily ultra-basic lithologies, but serpentine abound as well. most people, most investigators attribute the serpentines to erosion and did not as primary mineral, but as a secondary mineral, as look at it as intrusion and interruption rather than in contribution. The area can be small as 10 kilometers square and as large as 7,000 kilometers square. Very, very variable. Most complexes rise above the immediate environment from half a kilometer to 3 kilometers. I'll show some pictures. And the ultra-basic lithologies that I talked about here are presumed to be from the upper mantle to show the composition of the upper mantle. And the emplacement is attributed to very large, low-angle detachment normal faults, but there's another explanation which I'll try to describe here. The basic explanation of the mechanism of one oceanic core complexes is based on a simple shear model that was suggested by Brian Wernicke in the 80s, some 40 years ago, and it didn't stick. His physics wasn't very strong on that, so for several years there were discussions about, in the literature about simple shear and pure shear, and it didn't stick. But it stayed in the oceanic core complexes. It is believed that the oceanic core complexes come from here all the way to here, and they're deposited here. On top of many oceanic core complexes, there is a thick layer of rubble, which is attributed to the trip along here. There are two problems with this model. One is that some seismologists, here is your field, some seismologists like Chris Schultz from Columbia University argue that there are no data of low-angle normal faults. The degree, steepness of 25 degrees or less, he doesn't know any measurement of earthquake in this, under these characteristics, so this is problematic. Another point is the pressure here should be large, and we would expect in the oceanic core complex to show high pressure mineralogy like eclogite. There's none. There is none. So the conventional wisdom has its problems. The model, the accepted model, was suggested by Dan McKenzie. It was called pure shear. The material comes from bottom up. No hocus pocus, no low-angle normal faults. This is a chart of the central Atlantic Ocean. Here you see the map, and this is the area I'm talking about. There are several transform fault and fracture zones. Let me refresh your memory. Transform fault is an active plate boundary between this plate and this plate. The motion is the mid-ocean ridge marked in red is not offset. It jumps in its initial state, as I showed in the experiment that we did in Rennes with a sandbox, and it stays stable. So this part is stable, and when the plates move, from here on they move together. The scar of the valley of the transform fault, which according to Morgan and his team is due to oblique extension, remained embedded, and you can see the trace of the fracture zone all across the oceanic ocean. The mobile part is here. Earthquake occur only here and along the ridges. So the transform faults are marked in yellow, the oceanic ridges in red, the fracture zone in green, and the purple are the location of oceanic core complexes. Why would there be preference for slow spreading center for oceanic core complexes? Because we showed in the experiment of the subduction that I showed you before that you don't need compression to produce subduction. We could, but we didn't apply compression to our models in the centrifuge. Just put two materials, one next to the other, put some lubrication to reduce friction, put it in the centrifuge, rotate it for several minutes, and you get subduction. The denser material will come down, and the lighter material will ride on top and extend. And therefore, when you put fresh basalt, oceanic basalt here, juxtaposed against older basalt in the other tectonic slab, this will go down, this will ride up, and things will happen. I'll show you in a minute. Things will happen, and you don't need push to produce it. It's only even static. You let it go, and the denser slab will dive under the lighter slab. That's what we showed in model, and that's what we showed in theoretical model, and that's what we showed in analog modeling. And if the motion of the oceanic spreading is fast, then this basalt won't be heavy enough to drive under the lighter basalt, so you don't get subduction and you don't get the oceanic core complexes. This is a map of one of the oceanic core complexes. It's called the Atlantis core complex. Mid-Atlantic ridge is here, and latitude 30, 3010, 35, and 3010, yes. This is about 50 kilometers. Yes. It's quite high, about 1,500 meters above its neighborhood. And this is a more detailed map, and they were doing seismology in this area where these upside down purple triangles are the seismograph stations. There are several. And they found here two things. First, there were also dives here, observations, and dredges, and camera taken. So this oceanic core complex was very thoroughly studied. And they also put in some of the, not in this one, but in some other, no, they're also here. Oceanic core complexes in the Atlantic Ocean and also in the Indian Ocean, the scientific drilling operation were carried out. And I want to show you some results. And here you see the mineralogy if a borehole 1271A and 1271B. I think that Kellerman was the chief scientist. And there were two boreholes. This one was short, about 40 meters, and it recorded mostly dunites and some fault gouge here and near the surface. The other borehole, it went down to more than 108 meters. There's several ultra-basic minerals or rocks. We have the dunite, we have the Harzburgite, we have the troctolite, which is the volcanic version of the peridotite. And where the serpentine I talked about, no serpentine to talk to. But when you look at the cores, they are green. The cores are green, and they are built mostly, this part is built mostly of serpentine. Here you have ultra basic rock. So this is not a minor minor show of the serpentine. And the people who explored it considered the serpentine as some sort of alteration, a late alteration, and interruption to the original lithology, while you see that it is internal part. And as such, it can be the mobile part which will carry the ultra-basic rocks back to the surface, because this is light. And every oceanic core complex has its series of serpentine in large quantities. You can check the literature. Everything is in the internet. The results of oceanic drilling. This is from leg 209, but there were other legs as well. Here's a closer look. This is the serpentine, this is the serpentine, and these are the Harsburgat or the Dunite, I don't know. Now, if you want to see beautiful pieces of tough serpentine, not soft, but really tough, you can follow the footsteps of the minister of whatever, and take a look at the Dome of the Rock, Mizgad in Har HaBayit, and inside are beautiful columns of serpentine, green serpentine, amazing. And they stand like this, well, from the Byzantine time. You can see similar column also in Hagia Sophia in Istanbul. So this part is this part, and this part is this part. The blue is the upper, the red is the lower part. And here is a picture of one of the types of the serpentine. And this is a survey at Marathon Transform Fault at latitude 13 in the Atlantic, 13 north in the Atlantic, where they left their seismographs. Here, these triangles, reversed, upside down triangles, purple triangles, here and here and here and here and here and here, many. I worked once in Western Kenya. The people walk naked, and they count 1, 2, 3, 4, 5 much. Huh? So 1, 2, 3, 4 times 4, 5 much, many seismograms, and they measured in 6 months 250,000 of earthquakes. It's active, it's moving. And the section is not large. From here to here, that's all. Some are extensional. I marked the extensional one with a red circle. Some are compressional, and some are strike slip. And here you see the distribution with depth, and the earthquake occur at depth of 5, 6 kilometers, perhaps 10 kilometers, very shallow. Very, very shallow. Most earthquakes under the Dead Sea Rift are at 20 kilometers. So this is a section, this is the central rift, and the authors presume that there is some hot anomaly here at depth. This is 9.5 kilometers, depth of 6, 7 kilometers. So I want to show this section from A to B. Hypothetical. We have the fresh lithosphere, we have the old lithosphere, we have material from the juxtaposition partly goes down, changes to peridotite and sinks into the mantle, and part is serpentinized and comes back to the surface with pieces of the peridotite coming up with it. Or a more beautiful picture that I made. Here you see the serpentinite going up along the fracture zone, the fracture zone near the transform fault. This is the old, this is the new. And it goes down to about less than 10 kilometers. The gradient of 10 kilometers in this part is huge because I said that in subduction the gradient is 10 kilometers, 10 degrees per kilometer, or 30 to 40 degrees per kilometer. Here the temperature is 1200 degrees. This is melted already. So 1200, 1300 if you will, and let's call it 10 kilometers, then you have 130 degrees per kilometer, but it's more. It's more. So the huge thermal, and the pressure is low, so you don't produce eclogites under this condition. And let's explain why there are no eclogites in nature. That's all.
Thank you, Yossi. Questions?
I'm glad that I convinced you all and you all agree with me.
Why did you show the Turner results of the compressive earthquake? How it fits your story? I don't understand.
Which?
All these micro earthquakes
Oh,
of Turner from Georgia. How it goes with
this?
Yes. How it fits how does it fit the main story?
It shows that the major motion is not motion that comes from deep places. It would be 100 kilometers deep, but it is very shallow. The earthquake depict where most motion occurs. And here it occurs at a depth of 5 kilometers. Here, not you.
But this is because of the
5 kilometers.
But this is because of the oceanic complex. I mean, the compression is due to the flexion. The lower part of the lithosphere is.
Go ahead.
You have compression there. So how it fits at the end of the
Yes, this is true, but it's not only compression, we found the extension also, and strike slip also. So there's a very variable motion in this piece. Things move to all directions, and that's not what would you expect had you accepted the long detachment fault, the normal detachment fault that goes down to the mantle.
Yossi,
Okay.
why ignore the evidence for the kinematics of the detachment? I mean, you see it in the ocean. You see these corrugations, like these striations. There's evidence of low-angle faults there. You don't need Chris Schultz for argument. I mean, there are no earthquakes. It doesn't mean that there are no faults. We know that Chris Schultz can teach you that. So I think the simple explanation should rely on the simple observations, which are that the kinematics is of spreading direction.
Yes.
It goes in the spreading vector, and you want it to go 90 degrees from there.
That's not my research. I took it from Chris Schultz, who's an authority on faulting in earthquakes. And Chris argued that there's no such thing as low-angle normal faulting.
Okay, let's put Chris aside.
I don't know then. This is what I'm leaning on.
On the observations of the direction, the flow, the slip direction. You see it by structural geology.
Yes, the question is it low angle or is it normal fault, not normal fault?
There is low angle, there's no question, you just need to look
No,
at
no,
the evidence.
that's no question.
You can see it in the mid-ocean ridge, you can see it in Cyprus, but the question is now which direction is it going, which
Yes.
orientation, and it doesn't go in the direction that you try to force it.
Again, it wasn't my research, not part of my research. It fits. I adjusted my research to the results I found in the literature. And while the results that Schultz showed about the rareness, if not absence, of seismological data about low-angle normal faults, the other expert models take it for granted. I had some debate with it with colleagues from England. I didn't discuss it with Kellerman, but with McCabe and others in England. And they agreed to disagree, but they didn't have hard data that showed that they are alone.
So let's agree to disagree.
Yes.
And hopefully, maybe Mayor would stand here and give your version, or our version. How about that? Okay with the...
Okay with the
לא התכוונו עכשיו שיהיה פה שימוע.
מאיר, אתה לא מסכים למה שאני אומר?
גם טרוקטולייט זה לא קטן.
היית צריך לבוא למכון הגיאולוגיה, היית יכול לא להסכים לעוד דבר. דיברתי על הבקע.
רציתי. הייתי מנוע.
היית?
לא, רציתי לבוא. לא הסתיים.
עוד שאלות, more questions. The point I want to make is, besides what we talked about here, I think this work has some significance about the composition of the mantle. Because the composition of the mantle is based on the ultrabatic rocks that are exposed so nicely in the oceanic core complexes, and everyone knows they come from the mantle. But if they're not, and if it started as basalt and converted to less mineral of less silica, we have to think again about the composition of the mantle. It's not my field. I'm not going to do it, but I think this is the significance of this talk, beyond the suggested explanation for oceanic core complex.